For this problem, the switch in our circuit has been closed for a long time before opening at t is equal to 0. For t greater than or equal to 0, we need to find the Laplace transform of the voltage V0 t. So for this, our switch has been closed, and then it is being opened. So in here, we also have these inductors, and we have this M here, so we know that there's going to be some mutual inductance. We're dealing with time, so we want to convert this to the time domain. In converting this to the time domain, we're going to put our voltage over S. We are going to transform this capacitor to be Z of C is equal to, and this is normally going to be 1 over S times C for capacitance. But since this is going to be in the time domain, since it's already time equal to 0, we don't need to adjust that for this one. So instead, it's just going to be 1 over the capacitance. The capacitance here is 4 microfarads, and this is going to give us a capacitance of 250. Where our resistor is going to remain the same. This 2 Henry inductor is 2 Henries, but it's going to become 2 times S. And this 4 Henry is going to become 2 times S, and same thing, this 2 Henry will be a 2 times S. Now, when we look at this, we are going to have some current flowing through here. And the current flowing through here, like this, it's going to go over this way. Some of it is going to go this way, and some of it is going to go this way. So if I was to draw this a little bit cleaner, we would say that the current in blue is going up through here, through here, through here, and some of it splitting off this way, and some of it is going down this way. And then obviously some will be going into here. So knowing this, we can write a formula for it. Well, we know that there's some voltage over our inductors, so we'll just call this plus, minus, we'll call this V1, and because this V0 here, we'll call this plus, minus V0. And there is an important dot convention. This is in section, I think, 11 and 9. Has to deal with mutual inductance and dot convention. But basically the way the current flows away or into it determines the signage of our voltages and later our currents that are dealing with the inductors. So for this, we are going to be looking at our V1 first. Well, our V1's in the time domain, so it's going to be V1 S. And this is equal to the inductor right here, so 2H, and we're putting this in the time domain, so it needs to be DI, and we're dealing with I1 because we're on this side. This is I1, and this will be our I0. It's given to us as I0. I covered it with the V0, but it says I0. And this is divided by dt, because we're in the time domain. We'll have a minus 2H, and this minus 2H comes from some current being shared with this other inductor, and it's negative minus because of the dot convention, and then this is going to be di0 divided by dt. So that's how that is going to look. So we can continue on with this, and so h di dt, we are going to have 2, and then inside of here, inside of the h di dt, we are going to take the current time, so for t greater than or equal to 0, and we are going to subtract that from our initial time. So we are going to have S for the time domain times our I1, and this should also be a 2. I realize it looks like a Z, but that should be a 2. And we'll have S times I1, and then we're going to have a minus because we're subtracting from the start, and then in here we're going to have I1 and 0. And we will specifically have this negative right here. And the reason why we have this is because, well, if we look at a graph, we'll just draw one right here. When it's at 0, we can see that for t greater than 0, we're going to be going like this. For t less than 0, we're going to be going like this. Well, t is approaching 0 from the negative side when it is closed. So before our operation happens. So that's why it's a negative, and this would be a positive if we were approaching it from the positive side. Next, we have this negative 2 Henries to deal with. So we're going to have a negative 2, and this is for the mutual inductance. This is for self-inductance. Now we're dealing with the mutual inductance, so it's based off this. We have a minus 2, and then inside of here, we are going to have something similar, S times I naught minus our I naught, and then inside of here, we're going to have 0 to the negative. And this is going to be our equation. Now, there's a few things that we can find. We can find our I1. We're also going to find our I naught at 0 as well. First is our I1. For I1, we know that we have this voltage right here, and it's flowing over this capacitance. And so knowing that, this, we can use Ohm's law and say that I is equal to the voltage divided by resistance. And we know that voltage is 12 volts, and the resistance here is this resistor, so it's 10 ohms. And so the current here is going to be 1.2 amps. So we would be plugging 1.2 amps inside of here. Now for this I naught 0, the switch is closed. We have this capacitor absorbing. And so what that means is that for this I naught 0, we're just going to have 0 amps here. And so that is going to be our equation. Now we can rewrite this and factor in these 2's in. So we are going to get that we have a V1 of S, and this is equal to, first we have our 2 times S I1, and then we have a minus 2.4 amps, and then we have a minus 2S times I naught. And so this is going to be our V1 in the time domain for S. Now we are going to look at V naught S. And for this V naught S, we have this 4 henries right here. Now because of the dot convention, it's going to be a minus 4H, and we're multiplying this by d I naught this time because we're dealing in this part the self-inductance first, and this is being divided by dt. And then we are going to have a plus because of the way the current's flowing into the dot convention. And then we're going to have our 2H, and it's 2H not from this, but from this part right there. So 2H times our di1, because this is the mutual inductance, this is coming from the left side up here. And it's going to be over dt. So when we write this, we are going to have a negative 4, and then inside of here, we're just basically writing the same thing as we had up here. So we're going to have S I naught minus our I naught as 0 is being approached, and we know that this is 0 amps. And then we have a plus 2, and inside of here we have 7 S I1 minus I1 0. And we know that this is 1.2 amps. So when we rewrite this, we're going to get that our V naught of S is equal to, and then inside of here we have a negative 4 S I naught, and then we have a 0, and then we have plus 2 SI1 plus 2.4. And actually this should be a minus because I didn't see that minus there, but we'll have a minus 2.4. And so checking all that, this is going to be our V naught of S. Now we want to solve for the voltage over a capacitance, and then we could use the mesh current analysis to find the currents flowing over here. So for this, we're going to have our V of C, the voltage of the capacitance, what we want to find, be equal to, we know this is equal to our I1 times the capacitance, the impedance of the capacitance. So we're going to have V of C is equal to, our I1 is unknown. However, we do know that our V of C, which is this voltage, should have an S under it because it's in the time domain. So this will be divided by S, by the way. So we'll have an S under here, and it's being multiplied by the impedance of the capacitance, which is 250. So we are going to have V of C is equal to I1 250 divided by S, or we could say that our I1 is equal to a VC times S divided by 250. And so now that we know this, we could do the mesh current analysis. Next, we're going to be dealing with mesh currents. we're going to be adding the voltages in here. We're going to be dealing with this left side and then this right side. For this left side, we have this voltage right here. We can see it's going in the opposite direction of our current, so it's going to be a negative. We'll have a negative 12 divided by S. We have this capacitor next. We found the voltage for that right here. So we're going to have a plus I1 250 divided by S. Next we have this resistor right here. So we will have a plus I1 times 10. Next, we have all of this right here. And we found the voltage for this. We found it right here. We found V1, and to deal with the V1, because our V1 right here has already calculated all of this extra stuff, we are going to just plug in what we had earlier, which was this. We found our V1 here. So we are going to have a plus 2SI1 minus, and then I'm just going to put the back first, 2SI0, and then minus 2.4. And this is going to be equal to 0 per the formula. So now that we know this, we can combine some things. Now we're going to want to solve for our I0 of t, and so we need to find a formula for our I1. Well, we have this other side that we can look at for that. For this other side, it's going to be a little bit different. First, what we can do is we can, because we're still dealing with voltages, we're going to have the current of this whole right side, so I0 times the total resistance or impedance, which is this 4 and this 50. So the 4 Henry inductor and the 50 ohm resistor. We're going to add these together. So we're going to have a 50, or an I0, we're going to have a 50 plus a 4, and this 4 is an S. And we added this S earlier. From here, we are going to see that we have some current from our I1 this way. It's flowing into the dot. So we're going to have a minus. We're going to do a minus. We have this mutual inductance of 2S, so we're going to have 2S I1. And lastly, we do have some current. You can kind of look at it for the V0 S that we found earlier. And this is going to be plus 2.4. So that is what that will look like. And we can set this all equal to 0. So after this all equals 0, we can move stuff around. We're going to want to solve for I1 here so that we can plug it in to our equation up here. So we can write that we have an I0, we have a 50 plus 4S, and then we have a plus 2.4 divided by 2S, and this is all equal to our I1. So that is our equation, and then we could plug it into here. So from here we need to do some math. We're going to multiply both sides by this 2S, and then after we do that, we could factor this. We can say that this is our A, and this is our B, and then we could factor A and B over this, and do the same for B. So let's do this one at a time, or we can do them both together, because it's quite simple. So first off, we are going to have our I0, and we have this whole part together. So we have I0, but since we're doing this with our I0, we can just have the I0 factored out still. We have our I0 here, and in fact, if we wanted to, we could factor out a 2. But I'm going to just do it like this, and we have a 50 plus 4s being multiplied by this 2s squared. So we are going to have a 100s squared plus 8s cubed. And then we're going to factor it with this 10s. So we're going to have a plus 500s, and then we will have a plus 40s squared. Next we have this 250, and 250 times 50 is going to be a plus 12,500. We have this 4s, and 250 times 4 is 1,000, so we're going to have plus 1,000s. And so that's it for our I0. Next we have this 2.4 we have to deal with. So we're going to have a plus 4.8s squared plus a 24s, and then we have a plus 600. Now I did make a slight mistake, and I'll do this in red. When I multiplied the s out from here to make it simpler to look like this, well, I did it with this part. We can see that this is an s squared now, cancel out the s here. However, I forgot to add an s to here. So this is important. It's an error. There should be an s after this 2.4. So we'll have an s there and an s there. So when we write out this right side, it's going to be all of this. But remember, we still have this denominator we have to multiply by. So this denominator is going to have to be over here as well after we cancel it out from here. And so this means that we are going to have a 4s cubed I naught. We are going to have a plus 24s, and then we are going to have a plus 4.8s squared. Now, if we look at the left and right, we can see some similarities. This is 4.8s squared. This is 4.8s squared. So these will zero each other out. Same thing with this 24s. And this is what we're going to be left with. So knowing this, we can rewrite this. We can add like terms here, and then we can combine this I naught here, and then just move the 600 over to the right. And if we plug this into a calculator, this is what we are going to get. 150, and then we have this s plus 25, and this s squared plus 10s plus 125. Well, this s squared plus 10s plus 125 is a complex number. It results in it if we were to do the quadratic equation. So in doing the quadratic equation, this right here, we are going to plug in to a calculator right here. And then we could change this plus or a minus. So we're going to get slightly different values because of the conjugate, and this will just be changing plus minus. And that's based off of this. So we can write this out first. This is going to be equal to a negative 600, and then we have our s plus 25, and then inside of here we have an s squared plus 10s plus 125. So now dealing with complex numbers, this is going to give us this. We'll have a negative 600, and then if we use the Symbolab calculator, we are going to get two possible values. We are going to get first that, and I'll write this over here, s is equal to a negative 5 minus 10j. And so that is the first if we have a negative. And now if we switch our quadratic to be the positive part, we're going to have that s is equal to a negative 5 plus 10j. And so when we write this in, we are going to have our s plus 25, that does not change. And then in parentheses again, we are going to have an s plus 5 plus 10j. And then we are going to have an s plus 5 minus 10j. And so that is that. Now we need to do some differential equation stuff. We're going to set this equal to an a divided by our first part, s plus 25, plus the b divided by the next part, s plus 5 plus 10j. And then we are going to have a plus b, but this is the conjugate of our b. And we know it's conjugate because we had to use imaginary numbers. And we're going to have s plus 5 minus 10j. And so that are those parts. Now from here, we can solve for each part. In blue is what I'm going to solve for a. So for a, we are going to be multiplying both sides, and it's easier if we write this out first. So if we write this out, it's going to be a divided by s plus 25, and this is equal to a negative 600 divided by s plus 25, and then we have our imaginary numbers s plus 5 plus 10j, and then s plus 5 minus 10j. So we see that both sides have this s plus 25, so we can cancel them out like this. And in here, we're going to plug in what s would equal to make it 0. So to make this 0, s would equal a negative 25. And so we're going to use s is equal to negative 25. So if we plug this in here, we're going to get a negative 20 plus 10j. And then if we plug it into here, we're going to also get a negative 20 minus 10j. So when we factor these together, we're going to get a 400, and then we're going to get a plus 100. You see we have this 10j times this negative 10j, but the j's combine together and make a negative, so a negative times a negative is a positive, and this gives us 500. This means that we are going to have a negative 600 divided by 500. However, I have made a mistake, and this mistake is from me not looking at the calculator correctly. We see that we actually have a 150 up top here, not a 600. So it was a 600, but it was simplified, and now it is 150. So I need to correct that. That means that this should be 150, this should be 150, and then this should be 150. Also, this should be 150. So when we look at the answer for this part, well, we can cancel out the zeros. And then we can also have this negative 15 divided by 15, or 50. And so 50 divided by 15 is going to give us 0.3. So for this part, A is equal to a negative 0.3. And so this is this answer. And we are going to use this when we plug it back in to this right here to get our final answer. But before we plug it back in, we still have something to solve for. And it's this b right here. Now we don't need to solve for both b's. We only need to solve for one because we have the conjugate and we can just flip the angle. And that's also not going to be important once we do the actual theorem to convert it. So for our b, we're going to have b, and this is divided by an s plus 5 plus 10j. And this is equal to our negative 150, which I corrected, divided by s plus 25, s plus 5 plus 10j, and then we have a s plus 5 minus 10j. Inside of here, we can cancel these two out, and then, since that's what we were canceling out, we are going to use that to solve. So we're going to have that our s is equal to a negative 5 minus 10j, so the opposite. What made it 0. And so when we plug this in for here, we are going to get a 20 minus 10j. And then when we plug it in for here, our 5's are going to be zeroed out, and then we're going to have a negative 20j. And so in doing this, we're going to get a negative 400j, and then we're going to get a plus. We have this multiplied together, and this should actually be a negative because we have these two j's that combine together, and we'll have a negative 200. So this means that we are going to have b is equal to, we have a negative 150, and this is being divided by the negative 400j minus 200. So we can just write this in here, and then we can go over to Symbol Lab, and this is the free online calculator, and we could plug these values in, and that's going to give us this 3 over 20 plus I or j 3 over 10. So we can write this out. B is equal to 3 over 20 plus j times 3 over 10. But for our answer, I'm going to also separate this for clarity. We don't want it in the rectangular form, which is what it is in right now. And so to convert it to the polar form, we are just going to use the formula that our Vmax is equal to the square root of our real number squared plus the imaginary number squared, and then that our angle is equal to tangent negative 1 of our real number divided by our imaginary number. I made a mistake though. This should be the imaginary number divided by the real number when we do this. So it'll be the imaginary part divided by the real number. And this is going to give us a b is equal to 0.34 at an angle of 63 degrees. And so this is going to be our b. Now, we are going to plug these values back into our equation. We found our a and we found our b. And so we can say we have a negative 0.3 divided by s plus 25, and then we have a plus our b, which is 0.34 at an angle of 63 degrees, divided by s plus 5 plus 10j. And then we have a plus our conjugate. This is going to be 0.34 at an angle of negative 63. And then s plus 5 minus 10j. The conjugate just means you switch the angle degrees, or the signage. Not degrees, the signage is what you're going to want to switch. Now, if we look in the notes, I think page 50, there is a table, and in this table, it tells us that we can use this equation. We have e negative a of t is equal to 1 over s plus a. And we're going to use this to solve for a. We can see it's very similar. We're going to have negative 0.3 times an e to the negative, our a is 25, so we'll have 25t. And so this is going to be that part. And next, we have, we'll do it in green again, these b's. Now for this b, we're going to use a different equation. And this equation can also be found in the notes linked below the like button. And it's going to look like this. And so for this equation, what we're going to do is, well, we have this 2 times k. Our k, if we look to the left right here in the s domain, because we're converting from s to t, is this 0.34. So we're going to have 0.34 times 2. This is going to be a 0.68. We have an e to the negative alpha t. The alpha in this case is 5, so we're going to have negative 5t. And then we have cosine of our beta, and our beta here is going to be 10, no negative. So cosine of 10t plus our angle, no negative, is 63 degrees. And so that is that for the second part. However, these are not our answers. And that is because of one very important detail. And this important detail has to do with the units. I'm just going to paste the answers right here for now, so they're over there, but we'll delete them in a second. If we look at the units, it's in milliamps. Also important to note, we need this u of t because we are now in the time domain. But because of this milliamps, we have to convert our answer. So no longer will it be negative 0.3. Now it's going to be a negative 300. The exponent is going to stay the same, so we'll have a negative 25 here. We are then going to have a 680 here. Our exponent is going to be a negative 5t. This cosine is going to be a 10t, and then our degrees is going to be 63. And so that is the answer for this problem. And zooming out, we can see how we've done this problem. So first, we found the voltages here. Then we use the adding voltages mesh current method right here, and we used it right here. We substituted in the equations right here. We simplified it down and we got it to this form using the Symbolab calculator. We solved for each specific part over here, and then we used these last equations to convert them, and we found our answers here. And that is how we would solve this chunky problem.